Unfortunately, the last session that we had, I forgot to click on the record button at the beginning, so I wasn't able to recover the video from the last session. That's why I put up a version of a previous class covering the same material. The only bad part about that is it exposes the fact that I say the same thing every year. I'm not very original. So hopefully, if there's any references to dates or something like that, it'll be pretty obvious that you're going to be ignoring them because, if I tell you that the test is on October 3rd, I think you can figure out that that's probably another class, right? Exactly. So, okay, so you should see my screen now, I think, right? Yeah, I see it back here. Vicky, just confirm for me that you can see my screen. Okay, I'll move something around here. So, yeah, okay, good. That's terrific. We're set now. Um, so tonight we're gonna the first part of the class we're gonna cover. We're gonna back up a little bit, cover something that's going to introduce a special distribution called a binomial distribution. We kind of started on that before, and we're gonna start with kind of that little probability tree that we were talking about before. And but then we're going to move on very quickly from that to the normal distribution. So I'm going to start on that first. This is something that you pretty much really need to know and understand going forward in statistics, epidemiology. But it's really not so much the binomial distribution, but the normal distribution that you're really going to be applying much more for the rest of the semester. So I want to get through this part of it first, though. So I'm going to move this out of the way. I'm going to open up a page. And I'm going to start off by flying without a net. I'm not going to use prepared materials. I'm just going to open up a page here so that I can write. Okay, and I am recording. Good. All right, so let's see. You guys recall that when we were talking about coin flips, the idea that the first coin that we flipped could come up either heads or tails, right? And then if we took that coin, flipped it again, well, if it came up heads in the beginning, it doesn't know, it has no memory of what the result was. So the second time we flip it, it could come up heads or tails. Whoops. Undo works there. It could come up heads or tails. Right? Now, similarly, if it come up tails, the second crow could come up heads or tails. And then subsequently, the third toss, if it came up heads on the second coin, it could come up heads again, or it might come up tails. Or similarly here, heads and tails, heads and tails, whoops, heads and tails, and heads and tails. Okay, to make a long story short, we knew that each of these possibilities was 50-50. Could come up one heads or tails, either way, 0.5. So if we wanted to know, for instance, what the probability is that all three coins would come up heads, we would multiply 0.5 times 0.5 times 0.5 to get 0.125. And similarly, if we were going to do the same thing for heads, 0.5 times 0.5 times 0.5 for heads, tails, that would be the same probability, 0.125, 0.125, 0.125, so on and so forth. And in the end, we would see that there's only one way to get three tails, which is 0.125. So that's the probability of getting three consecutive tails. Now, there's only one way of getting three heads, right? That would be 0.125 would be the probability of getting that also. But there's several ways of getting two heads and a tail, or two tails and a head. Heads, tails, heads, tails, heads, tails, heads, heads, and so on. So there's many ways, three ways, in fact, of getting two heads, three heads, and two heads and one tail, right? So that probability of getting that result would be 0.375. And the probability we would add, these are exhaustive, right? This is all the possible outcomes that we could have. By the way, you could do the same thing with a dice and figure out what's the probability of getting a 7 on any roll, right? You could get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, 1 and a 6, a 2 and a 1, a 2 and so on and so forth, and work those out. And you'd realize you have 36 possibilities. And of those 36 possibilities, you have only a certain number of ways to getting 7. So you could figure out what the probability of 7 coming up on any specific roll. Okay, or how about 11? 11's an easy one. You have 36 possible ways for a combination of 2 dice. 11 can only come up, let's see, there's only 2 ways to get that, a 5 and a 6, right? And a 6 and a 5, right? No other way, there's only 2 ways. So the odds of it coming up are 2 out of 36, which is 1 over 18, right? Anybody ever play craps table? The craps table? What's the payoff on 11 on the craps table, right? They have a big number 11 in the corner of the craps table, right? In fact, whenever the 11 comes up, everybody yells "yo" right, at a craps table. Let me see if I can show that to you. Okay, so let me see. I'm not trying to turn you people into gamblers. It's just a convenient way to talk about probabilities. Here we go. Let's see this one. Okay, where's 11? Where's 11 on here? Do you see it there? Is that it down here? 11, 15 to 1. Field, yes. Oh, yeah, but field is any one of those numbers win. Let me see if they got one that's a little bit easier to see it in. This is 7 pays 5 to 1. Okay, 11 is that's craps. There's 11 on here. Should be here somewhere. Usually it's pretty prominent on most of these. Let's look at it here. Okay, 10, 9 does a. Here's 11, 15 to 1. Pays off 15 to 1. What are the odds of it coming up? 18 to 1, right? So the odds are coming up the odds of it coming up are 15 to 1, right? Which is, right, let's see, 15 to 1. 1 divided by 15. Probability on any given roll of it coming up is about 6.6%, right? But the payoff is 1 divided by 15, which is, well, I'm sorry, I gave you the payoff. The actual odds of it coming up are 1 divided by 18, which is only about 5.5%. So your disadvantage is like more than 10%, right? So the house is going to win most of the time. That's a pretty bad bet on a craps table, that 11, right? Similarly, 7. Let's see how many times would 7 come up. Well, you get the idea here. There, you can evaluate what all the possible outcomes are, and you can determine what the odds of those coming up are. With a coin, a little bit different than a die. A coin only has 2 possibilities: heads or tails. When we have an outcome like that, we call that a binomial outcome, right? 2. Binomial means 2. Okay, so it's interesting that, that a coin is a 50-50 kind of prospect, right? There's a lot of binomial outcomes that are not 50-50. For instance, let's say that I gave you a similar example to this in which you are going to answer questions on a test, right? And there are 5 possible answers, A, B, C, D, E, and you have no idea what the answer is, so you're just going to answer randomly, right? So on the first question, you could either be right or wrong, right? So you could be correct or you could be incorrect in your first reply. What's the probability, if there are 5 possible outcomes, what's the probability that you're correct? Well, it's only 1 in 5, right? So it's going to be 20%, right? Probability you're incorrect is 80%, right? Or 0.8. Okay, so now if you're correct on the first one, what's the probability that you're correct on the second one? Same deal, 0.2, right? And incorrect is 0.8. Same here, correct, incorrect, 0.2, and 0.8. This is still a binomial. The only thing here is that the odds of the 2 different outcomes are different, right? So on a third one, correct would be 0.2, incorrect would be 0.3, 0.8, correct 0.2 incorrect, 0.8, and so on and so forth. Similarly, if we wanted to know what's the probability of getting 3 correct in a row, when you don't have any idea how to answer the multiple choice question, it's 0.2 times 0.2 times 0.2. So similarly, with similar outcome for the heads and tails, but in this case, 0.2 times 0.2 is 0.04 times 0.2 is 0.008, right? Right. So, and similarly for 3 incorrect. And then for each one of these other outcomes, you can determine the probability of you getting 2 correct and 1 incorrect, or 2 incorrect and 1 correct, right? And you'll track this, with each one of these probabilities. Like this particular outcome might be for correct, incorrect, 0.2 times 0.2 times 0.8 would give you that one outcome, right? 2 correct one, and so on. You'd add up all the similar outcomes. So it works kind of the same way. Well, the only difference is that when we're using a coin, the probability of heads or tails is 0.5. In this one, the probability of a correct answer is 0.2. Okay? So now I'm going to take this tree, and I'm going to turn this tree sideways. And I'm going to say, let's say that instead of a coin, we're going to work with something where the probability is 0.5. Right? Except instead of a coin, I'm going to drop a steel ball, a ball bearing, straight down. And that steel ball is going to hit a pin. Right? Well, what are the odds that it's going to go to the left or to the right if I drop it right in the middle of the pin? It's 50-50. Could go to the left, could go to the right. Okay, now let's say it goes down to the right, hits that, bounces off, goes to the right. There's another pin over here, and there's another pin on this side. Well, when it hits this one, similarly, the probability that's going to go left is 50%. Probability it's going to go right is 50%. But just like a coin, the probability that it's going to make all left turns or all right turns is a lot less than it's going to find some other path down here, right? What's the most probable? Let's say there's 10 rows of coins. What's the most probable outcome in this situation for left turns and right turns? How many left turns and right turns? What do you think would be the most common thing to happen if it's 50-50 left turns and right turns? Where would it wind up down here? How many left turns would it make? How many right turns would it make? You figure the most, what's that? 5, right? Same number of left turns, same number of right turns, which would be put it just directly below it. What's the next most likely outcome? Well, 4 left turns, or 4 or 6 or 4 right turns, right? And the next most likely. Well, let's kind of draw that the way we would draw a histogram, right? It's going to look something like this, right? You're going to get a distribution. That distribution is most of the outcomes are going to be towards the middle. So we're starting to see that when we take large samples, and the larger sample we take, the more predictable that this outcome is going to be, this binomial outcome is going to be. If I drop one ball down here, I'm only going to get one result. But if I drop 1,000 balls down here, I would expect to see this pattern emerge. Well, lo and behold, somebody actually built a machine that does that. Okay, we're going to take a look at a movie right now. Okay, so you guys online, you're getting this as well? Okay, good. So we're going to look at a machine over here. It's called a Galton machine. Obviously, it was invented by a statistician called a mathematician called by the name of Galton. You can actually go and see this machine. I'll tell you about it, in a second. Let me open this up. Hopefully, you guys at home will be able to see this as well as we see it.
Can people still operate this machine?
What's that?
Can people still operate this machine?
No, I'm about to run it myself over here. Okay, hang on a second. Be patient. I'm going to let it run. Well, let me turn down my sound here. We don't need the sound. Okay, so what do we got going on here? Oops. I got to stop that. I want to go back here. Okay, let me stop it when it gets close. There you go. See the balls are coming down here? Right, and hitting pins and going left and right, left and right, left and right, and so on. All the way down to the bottom. So I'm going to let it go until we get close to the bottom. Okay, you can see them making left and right turns and so on and so forth. Let's see the result of this. There we go. Right? Pretty interesting, right? There is our result of this distribution of left and right turns that are based on probability, based on this binomial probability. And where are the most of the balls? They're in the center there, towards the middle, and there's fewer and fewer outcomes that are mostly left turns, mostly right turns, right? So that is a binomial. This is called a binomial distribution, right? It's simple probability, chance, that determines whether the balls are going to the left or the right. Now, where can I apply something like this? Well, let's say I'm interested. Let's say I'm dealing with a population that has 10% of the people in that population are diabetic, right? So I said to myself, well, gee, I'm going to open up a clinic. I'm going to have 100 people in here a day. I'm going to screen them for diabetes. And these people, they're going to be random people walking into here. And I want to have sufficient literature or supplies to give to people that I test that I suspect are diabetic, right? So how many people do I expect on any given day to be diabetic? So you know the prevalence in the population. The odds of any particular person having diabetes that walks in that door is 10%, right? So if you have 100 people what do you think the most likely outcome would be if you have 100 people walking in, right? Right? 10, right? 100 people, 10% prevalence. You would expect 10 out of 100 people to have diabetes. Well, that's interesting. But now I want to have enough materials and supplies and so on and so forth for, um, uh, for let's say, I really got to be prepared, but I don't want too much of an inventory. Let's say I want to be sure that 90% of the time I have enough kits here for anybody that will walk in that's diabetic. Well, half the time you got to have fewer than 10 diabetics. Half the time you're going to have more than 10 diabetics, right? The prevalence is 10%. 10 is the most likely outcome, but it's not the only outcome. It's the average outcome, right? So on any given day, you might get 7, you might get 12, you might get 2, but that would be very unusual, wouldn't it? Because that would be that kind of like a ball making all left turns and so on and so forth, right? So based on the prevalence, we can create a distribution that represents these probabilities. Okay, you can do this 2 ways. One way is you can actually calculate all of these left and right turns based on 10% and figure out for what's the probability of 1 out of 100, 2 out of 100, 3 out of. That's pretty tedious though, right? To have to do that, right? In fact, let me show you a formula if I can find it. Okay, let me finish that. By the way, excuse me. Anybody have any idea where this is? You guys online? You have any idea where this is located? Oh, does it say on there? Yeah, good idea. It's at the Queens Museum of Science, the New York Museum of Science, the whole New York Hall of Science here at Flushing Meadow, right, where the old World's Fair used to be. What's that? Oh yeah, it's there, still there. Yeah, yeah. It's a giant building. They have like rockets there on the outside and all sorts of stuff. They have a whole floor section devoted to mathematical stuff, and another area optics, another area all kinds of other. If you have a kid, it's a great place to go to because there's a ton of hands-on stuff. And in fact, when I was filming this, you might see a few kids back there, but excuse me, as it got towards the end of this, right, as it was starting to run out of balls, you had a bunch of them. You can't see them. They're sitting on the floor behind here, and they're waiting to see what happens when it runs out of balls and it flushes, right? So they were pretty excited by this thing. So yeah, so you can actually go over there and see this thing and a whole bunch of other demonstrations, including some other probability demonstrations. So at any rate, so that's our Galton machine. So now what about calculating this? Well, one way to calculate it is actually do the exercise that we did with the probability tree before, where where left is diabetic, and that's only 0.1%, 0.1, 10%, and right is not diabetic, which is 90%. So let me go here. Okay, so an alternative to actually doing that is representing that as a formula. Okay, and here it is represented as a formula. Okay. All right, so what does this say? The probability of our outcome, whatever our outcomes happens to be, right? The probability of the outcome that we're interested is equal to, this is a special kind of factorial. It's called combinatorial. Rather than explain that, this really translates into this formula down here, where n represents the number of trials. Like, for instance, in the thing I just told you about, the number of trials was 100. 100 people coming in. What's the probability of getting 10 out of 100? So n is 100. X represents the successes, when what you're looking for actually occurs. So, for instance, whether or not a person is diabetic or not, right? So this would be 10. So that's 100 factorial divided by 10 factorial minus 100 minus 10, 90 factorial, times the probability of not being diabetic, which is 0.1, or the probability of not being diabetic, which is 0.9, and so on. So that you would use that formula. Obviously, doing this is going to be pretty tedious as well. So what will we do now? Well, we have a tool which will actually help us with this stuff. And one of those tools is a lozenge, so I can actually, my voice will last a little longer. It's taking me a while to get over this cold. Okay, so we're going to open up Excel. You can do this with me if you want, or you can just watch me. Okay, so now what I'm going to do, I'm going to make this a little bit bigger. I don't want to make it too big, I want to make it a little bit bigger. Okay, so instead of, let's talk about slightly different, smaller number of possibilities here. And let's see, let's say that the prevalence of diabetes in the population, well, I'll use the example that we're just talking about. Yeah, that'd be too tedious. Do it a little bit differently. Let's say the prevalence of diabetes, it's a special population. Prevalence of diabetes in the population is 20%. Right, 0.20. Probability of a person being diabetic is 20%. I'm going to sample 10 people randomly from this population. So my n is equal to 10, right? So I want to know, for instance, what's the probability that all 10 would be diabetic? That's easy. It's going to be 0.2 times 0.2 times 0.2 times 0.2, 0.2, 0.2. What's the probability none of them are going to be diabetic? That's easy too. 0.8 times 0.8 times 0.8 times 0.8, and so on. The hard part is, what's the probability that exactly 3 out of 10 of those people are diabetic? That gets a little tricky, doesn't it? Okay, so if I look at this, the most likely outcome here is going to be 2 people out of 10, right? So because the probability is 20%. So I need to figure out a way to figure out all the different possibilities that are going on here. I'm going to start with, let's see, what's the probability none are diabetic? What's the probability 1 is diabetic? 2, 3, 4, 5, 6, 7, 8, 9, or all 10, right? Those are all my different possibilities for 10 people, right? Most likely outcome is going to be 2. Let's do that first. What's the probability exactly 2 people out of 10 are going to be diabetic in this population? Well, wouldn't it be nice if Excel had a function which would solve this equation for me? And in fact, it does have a function that will do that. Equals binom dist parentheses. Now, notice what it asks me down here. It's going to be a little easier on your own computers to read this because it's so tiny. It's asking for me to the number of successes. Remember what I call the success? I call the success the number of times you find what you're looking for. In our case, diabetics. So this seems a little odd to say that a person with diabetes is a success, but that's what we're after here, a number of people. So in this case, I'm looking for 2 people that are diabetic, comma, right? Actually, you know what I'll do? Instead of doing it that way, I'm going to click in here. And that's really, we know that that's 2 anyway. So comma, what's the next thing it wants? The number of trials. Well, the number of trials is your sample size, number of people that you're testing. In this case, it's 10, right? 10 people that we're looking at. N is 10. And the probability of success for any person in any particular person in the population is 0.2. The next thing it asks for is something called cumulative. And then I put a comma in there. Next thing it asks for is something called cumulative. I got 2 choices to this. I can say true or false. I'm going to say false. And we'll figure out why I said false in a minute. Okay, I'm going to hit enter. The probability of exactly 2 people out of 10 being diabetic, if I have 10 people or randomly sample 10 people in this population, is about 30%. Okay, what if I want to know exactly 3 people? Equals, well, I can do the same thing, equals binom dist, parentheses, okay, and oops, I misspelled it. And the number of successes, in this case is 3, the number of trials is still 10, the probability is still 0.2, and again, I'm going to say false. And don't worry about why I'm saying false here for the moment. Close parentheses. Now, what do you think that's going to be? Is it going to be a bigger number or a smaller number? Bigger probability or a smaller probability than 2? It's going to be smaller, right? Because the most likely outcome is 2. And in fact, it's down to 20%. Okay? And if I want, I could actually, since I use this as a formula in here, I could actually drag this down and have it calculate all those probabilities. Look, the probability of getting exactly 10 out of 10 is teeny tiny, right? It's 0.2 times 0.2 times 0.2 times 0.2, and so on and so forth. Wow, how about going up? I don't know if it'll let me do that. What's, I'm sorry, say it again.
It says for 8, 9, and 10, it says E-05.
Yeah, what this is
like an error?
No, it's not an error. What it is it's a function. In other words, since this is becoming such a small number, it's giving it to you in scientific notation. 7.3 times 10 to the minus 5. The E stands for exponent of 10. Okay, or 4 times 10 to the minus 6, or 1 times 10 to the minus 7. 1 times 10 to the minus 7 is really, move the decimal place over 7 places. It's 6 zeros with a 7 at the end after the decimal place. It's 0.00000007. Okay, so it's very, very tiny likelihood of that outcome. Now, it's very interesting to know exactly what the probability of exactly 5 is, right? Or 3 is, and so on and so forth. But really, what might be more interesting to us is what's the probability of getting, say, 2 or fewer, right? 2 or fewer. So probability of getting 2 or fewer is the sum of these 3 probabilities. So the probability of getting 3 or fewer people that are diabetic, 2 or fewer people that are diabetic is 67%. Okay? Sure. I just use sum. Okay, let me hit escape. Oh. Equals sum, parentheses, and I'm going to put in the cell for 2, 1, and 0, D2 through D4. Enter, and it's going to add those probabilities together, and it's 67%. So what does that tell you also? The probability of 3 or more people is going to be what? Is going to be the difference between 67% and 100%, between 0.67 and 1. It's going to be the probability of getting 3 or more people that are diabetic is going to be the sum of these probabilities. But what do all these probabilities add up to? Yeah, it adds up to 1. Well, as probability adds up to 1 or 100 if you look at it as a percentage, right? So if the probability of 2 or fewer is 67%, the probability of 3 or more is 1 minus 67%. Okay? Well, SBS, excuse me. Remember I used that expression. I'm going to do that. I'm going to do it for this also. Equals to sum. Parentheses just shows true. Okay, and if you add those two together, it'll add up to 1. Okay, so now there's a little bit of inconvenient to have to do this if we're doing it for many more possibilities, could get a bit inconvenient. But now there's another way that you can do this. Okay, and for instance, if I wanted to know what's the probability of having 4 or fewer diabetics in my sample of 10 people, I'm going to use the same formula, equals binom dist, parentheses, right? The number of successes now is going to be 4, right? Comma, trials. Trials is going to be 10, right? Because that's my sample. Comma, yes, Vicky, you got that right. Comma, a probability is going to be 0.2 again, comma, except this time I'm going to say true. And what is true got to the term cumulative? True now is going to give me the probabilities for 4 and everything less than 4. So it's going to give me 96%. And if I go over here and actually do it this way, parentheses, and add them all up, I get the same thing. Okay, pretty good, right? Saves you a lot of trouble when you're doing calculations with binomial distribution. So you might get a question on a homework or a test or something like that that might ask you, for instance, given that the probability of this outcome is 20% and you're going to sample 32 people or something like that, what's the probability that you would get 3 or fewer, right? So 3 or fewer would be 3, comma, whatever the number is, 3, comma, 20, comma, 0.2, comma, and then true for cumulative to get the number less than that, 2 or less. Like for instance, as we did here, right, 4 or less. Okay, now I might ask you, what's the probability of getting, say, 3 or more, right? 3 or more, or all of these possibilities, right?
So when it's more, it's false, and when it's less, it's
No. When it's false, when you're only looking for that exact outcome, right? In other words, exactly 3 out of 10, right? But they use false. If you're looking for a range, everything from that outcome down to 0, right, is going to be true, cumulative. It builds up from the bottom. Okay, so now let's say I ask you, in this case, for instance, what's the probability that you would get 3 or more diabetics? 3 or more. Well, 3 or more would be all of these possibilities, right? So I could add all of them up and get an answer. Which did I already do that? Did I? Is that what this one was? 0.96? I'm not sure. Well, let me do it. Okay, let me do that. Let me get rid of this. 3 or more is going to be equal to sum, parentheses, and 3 or more is going to be all these guys here. So it's, whoops, yeah, 0.32. I didn't, yeah, we did do it in one form over here, right? That's the probability of getting 3 or more diabetics, right? 3 or 4 or 5 or 6, any of those satisfy me, right? So 3 or more, how would I do that with the cumulative function? Well, equals binom dis, right? But it's going to not add up upwards, it's going to add downwards. So I only want the ones that I'm not going to include. So what should I put in here for my successes and cumulative? What do you think? Should I put in 3? No, 3 is going to be included if I put in 3 and go down. Should put in 2, exactly right. So I put in 2, comma, 10, comma, 0.2, comma, true, right? And that'll give us the percentage for 2 or less. And in order to get the percentage for 3 or more, I say equals 1 minus that value. Okay? So you can manipulate this a lot of different ways. But that's our binomial distribution. Okay? So you guys online, are you comfortable with this?
Professor, can you just go back to G, the cell that you just did, to get 3 or less? I can just see the formula.
It was just simply equals 1 minus G5. Yeah, right. This is the probability of getting
2 or less.
this is the probability of getting 2 or less, right? And so I just subtracted that from 1 to get 3 or more. Okay. So you kind of have to listen to the wording and interpret what actually you need. It's true for cumulative and sum is really. Well, some I only use some so that, like, normally when you solve a problem like this, you won't bother doing the individual outcomes for every possible outcome. You'll just do whatever you need to do using the cumulative or the cumulative true or false. So you wouldn't bother with this. Like, for instance, if I asked you now, what's the probability of getting exactly 6 out of 10 people? You would ignore what you'd use equal binom dist, 6, 20, 0.2, false, because you only want exactly that outcome, 6 out of 10. If you wanted to know 6 or fewer, you would use a binom dist, 6, 10, 0.2, true for cumulative, so you'd get the sum of all probabilities for 6, 5, 4, 3, 2, and 1, because 6 or fewer satisfies all those possibilities. And if you wanted more than 6, you would do the probability for 6 or fewer and then subtract it from 1 to get 7, 8, 9, and 10. Okay. All right. So what I'm going to do now is on Blackboard. There is. Let me go to Blackboard now. So what else I got here that I want to make sure I don't lose sight of here. You can also use tables to solve these problems, but for the most part, we're going to be in a situation where we're going to have Excel handy or a form of calculator handy, where we can stick with using the functions built into Excel. Just like before, when you saw that formula N, and I think they used R instead of K, but N and K, the number of successes. If N is, for instance, and this is I only put up one page of this table, but for instance, if N, the number of trials, is 7, the probability is that you would get exactly, 2 out of 7, and so on and so forth. Okay, given the probabilities, like 20%, you'd have all these outcomes and so on. So this is that what they basically did here. It's as if we ran Excel for every different possible, or many different possible probabilities and outcomes. But for the most part, rather than using a table, you're probably using Excel, much more flexible. Okay, let's just go through a couple of problems here. Okay, so let's look at these as kind of word problems here. We don't necessarily have to pull up Excel. You can, in fact, as I go through them, you might want to pull up Excel and solve them for yourself. Okay, let's wait for Word to be happy here so that it'll let me scroll. Okay, a study indicates that 10% of nursing home patients are diabetic. Oh my goodness, it's basically the same thing. Let's not do that one. Yeah, it's got sample size of 10. Let's skip that one. Study indicates that 4% of American teenagers have tattoos. You randomly sample 30 teenagers. What is the likelihood that exactly 3 will have a tattoo? So if I use the binomial distribution, it's going to be binom equals binom dist, parentheses, and number of successes is going to be 3. The number of trials, comma, the number of trials is going to be 30, comma. The probability of any individual having it in that population having a tattoo is 0.04. Is going to be 0.04, comma, and then what are we going to use there for there? True or false? Well, since we're looking for only the exact outcome 3, we're going to say false, right? Okay, how about 3 or fewer equals binom dist, right? Parentheses. 3 or fewer, 3 successes, comma. The trials is 30, comma, 0.04, still same probability, comma, except this time we'll say true, so we will get the probability for the sum of the probabilities for 3 out of 30, 2 out of 30, 1 out of 30, or none out of 30. Okay, and then finally, 4 or more will have tattoos. Well, 4 or more, we just figured out what the probability of 3 or fewer of these people having tattoos, right? So what's left outside of the 3 or fewer, the other possibilities are 4 or more. So we're just going to get our result from 3 or fewer, subtract 1 from it, so subtract it from 1, and that'll give us the probability for 4 or more, the rest of the people that are in that population. Okay, so Poisson's distribution, I'll discuss later on, but I think we can move on from here and get into some other stuff at this stage. What I'm going to do now is I'm going to go to Blackboard, and I want to play the there's a PowerPoint and a associated lecture that gets into this from another perspective and also starts you on normal distribution, right? So I'm going to play that now here. So you guys online, you have the choice of either playing it for yourself separately, or I don't think it's going to work very well to broadcast this. So it may be better if you just watch it yourself. Like in other words, I'm going to click into Blackboard. I'm going to go over to, let's see, sessions, session 4. And I'm going to go into and start this this PowerPoint. This first of all, I'm going to open up a PDF, which has the. I didn't mean to do that. Oh, that's okay. I'll do it this way. This is the PowerPoint. You can see the material that we're going through over here, and it's an introduction to the binomial distribution, a little bit of probability, and the normal distribution. So when we're done with this, we're going to come back and we're going to go over all this material from the place where we've just stopped. We're going to leave the binomial distribution and go into the normal distribution, which has a lot of similarities, right? They both have bell shape. They're both bell-shaped in many cases. They both have similar properties in some cases, but they're not the same distribution. Binomial distribution strictly for binomial outcomes, and the normal distribution we're going to use with numerical variables. Okay, so I'm going to. Well, when we're discussing histograms, we noticed that when you had a normally distributed numerical variable, we noticed that it was quite common that the distribution would be such that you get a lot of the values that are in the center. A lot of the people's values, a lot of the results are in the center, and fewer of the values are away from the center of the distribution, away from the mean for that population or for that sample. So we used to wind up with something that looked kind of like this. Maybe it wasn't perfect. Maybe you had a little thing over here, or maybe this was a little lower over here, and so on and so forth. But in general, that's kind of distribution that we're looking at. So for instance, the height here might represent the number of people, or what we call the frequency, right? And this might represent the value. Like if we were talking about blood pressure, maybe this represented 100, 110, 120, 90, 80, and so on and so forth. But if it was normally distributed variable, you'd expect a lot fewer people that were at the low end, a lot fewer people at the high end, and most people in the middle. You'd look at the same way at heights, right? People are normally a certain range of heights. It's unusual to get people that are much shorter or much taller, right? Now, if I were to break these up into and increase the sample size here enormously, and break these up into shorter and shorter intervals, like instead of a group of 10, a group of 1, each bar represented one value. So 101, 102, 103, and we took a very large sample, you would start to see this even out and form a curve like this. That distribution, this curve represents the distribution of values for this population, right? This is everybody in the population is in here. The mean is, of course, if it's normally distributed, the mean by definition is in the middle, right? So if I were to ask you what percentage of the people in this population have a blood pressure less than 100, what would you tell me? What do you think? Yeah. 50%, exactly right. What percentage more than 100? 50%, right? That's pretty obvious, right? That's because one of the properties of the normal distribution is that it's symmetrical about the mean, right? So it's the same number percentage of people below the mean as above the mean, practically a definition of the mean. Okay, so now we in fact can tell, we actually know even more about the normal distribution than this. In previous classes, we've learned how to calculate the mean, and we've learned how to calculate the standard deviation. Okay? And there's reasons why we're looking at those with such interest. And that is because those two values can define the way our population is distributed. So if I were to look at, say for instance, I just want to make sure I'm recording here for a second. If I were to give you a situation where the mean height for men is equal to 65 inches, right, with a standard deviation of, standard deviation of 3 inches, we could actually describe this normal distribution. In other words, the middle of the distribution is going to be 65 inches for this population, right? Now, the standard deviation is going to tell us the spread. Almost all of the values for a population is within 3 standard deviations below the mean and 3 standard deviations above the mean. So if the standard deviation is 3, that's 9 inches, right? So almost everybody is going to be between, let's see, 9 is going to be 56, and 9 more than that is going to be 74 inches, right? So in this population, almost everybody, 99.7% of the people are going to be between 56 and 74 inches. There's going to be a few taller people, a few shorter people, but most of the people are going to be in here. In fact, the largest portion of people is going to be in this area here in the middle. Look how big an area this is here, right? That might represent 1 standard deviation, or 62 to 68 inches tall. And that, in fact, we happen to know that based on the way normal distributions are structured, that represents 68% of the population. That's between 1 standard deviation below the mean and 1 standard deviation above the mean. Well, because we're defining the proportion of people or the probability that we would find a result in some part of this normal distribution as mean and standard deviation, we can actually apply that to any normal distribution. For instance, if we have another normal distribution where we're talking about blood pressure, and the average, say, mean blood pressure is equal to 120, right? And the standard deviation of blood pressures is for population is equal to 10. Well, then we could draw another distribution, right? Maybe it'll look like that, except this time 99% of the values are going to be between 3 standard deviations below, which is going to be 80, and 3 standard deviations above, which is going to be 150. So we can apply this same rule to all normal distributions once we know what their mean is and what their standard deviation is, what sigma is. I should really, for the moment, I'm going to use sigma and mu because I'm going to be talking primarily about populations for now. When I'm talking about samples, instead of mu, I'm going to use x bar, and instead of sigma, I'm going to use standard deviation. Okay, so for now, I'm going to call the standard deviation sigma and the mean mu. Okay, anytime you see me use those Greek letters, I'm talking about a population. Okay, so I'm going to open up a Word document that we have here. Normal distributions, empirical rule, and if you were following the presentation that Levi just did, the lecture that Levi just did, you'll have seen this drawing before. So for normal distributions, okay, and I'm going to round this off a little bit. This is a little bit more precise than we need to have to be for something called the empirical rule. For normal distributions, 68% of the values, the heights, the blood pressures, the blood sugars, the blood lead levels, whatever you're looking at in terms of a numerical variable, providing it's normally distributed, 68% is going to be between one standard deviation below the mean and one standard deviation above the mean. Now, that's going to leave, that's 68%, that's going to leave 32%. So 16%, if you add all this up, 16% is going to be below one standard deviation below the mean. In fact, if you look at 2 standard deviations below the mean to 2 standard deviations above the mean, add all these up, it comes out to 95%. 95% of the values are between 2 standard deviations below and 2 standard deviations above the mean. What about that we mentioned 3 standard deviations? Well, 99.7% of the values are going to be within 3 standard deviations below and 3 standard deviations above. Again, not many people are going to be more than 3 standard deviations away from the mean, either in the positive direction or in the negative direction. So we can take advantage of this to help us understand and predict the probabilities of picking out an individual with a certain value in a population, or the distribution of values within a population. Let's do a couple of examples. Assume that the heights of adult Caucasian men has a mean of 68 inches, mu, and a standard deviation of 4 inches. Find the probability that a randomly chosen individual from this population has a height greater than 68 inches. What do you think the probability is that they have a height greater than 68 inches? Right? The mean is 68, right? So what percentage of the people are more than 68 inches? Right? The mean is 68. Be half, right?
Yeah.
Right. Half the people are greater than the mean, half are less than the mean. So the probability that if we pick a random person from this population that they're going to be taller than 68 inches is 50%. Okay, so I don't even really have to do anything to really determine that. Right. Thanks, Vicky. You got it too. Okay. So let's take the next step here. What's the probability that the heights are going to be between 64 and 72 inches? Well, remember, 4 inches is the standard deviation. So 64 inches is 4 inches less than 68. So that's 1 standard deviation below the mean. And 72 is 1 standard deviation above the mean, right? So they're within 1 standard deviation of the mean. So what percentage is going to be between those two values of 64 and 72? 68%, exactly right. Good. Thanks, Vicky. Okay. So now, how about between 60 and 76 inches? I'll leave that up to you guys. Right?
60 and what?
Between 60 and 76 inches. How many standard deviations below the mean is 60? 95, exactly right. See how easy this is? 95% of the values are between 2 standard deviations above and 2 standard deviations below 60, which in this case is 60 and 76 inches. Okay, so let's move on with this. Assume that the heights of adult Caucasian women has a mean of 63 inches, standard deviation of 3 inches. Again, greater than 63 inches, going to be 50%. How about greater than 66 inches? I threw a little curve out there, didn't I, this time? Right? Let me get the my sheet here. Yep. Yeah, hang on a second. Now, as these get more complicated, this isn't really complicated yet, but as these get more complicated, it's worth drawing these out and shading them because it'll help you understand it. So, what did I say the mean was for the height of the women? Whoops. I want to scroll this up so I can see it at the same time. Okay, let me get my sheet back here. Okay, so I said my mean was going to be 63 inches. Okay, 63 inches. Mu is equal to 63 inches, and my standard deviation is equal to 3 inches. Okay, and 63 inches we decided was greater than 63 inches is going to be 50%. Okay, how about greater than 66 inches? 63, this is 66 inches, right? So we want greater than 66 inches. We want this area here. Well, the empirical rule only defines areas inside of this area, right? So 66 is how many standard deviations above the mean? Just one, right? 63, only one. So this is one standard deviation above the mean, right? So that means that this area, one above and one below, would be 68%. And since this area, since the normal distribution is symmetrical, that means that this is 34% and this is 34%. So how much does that leave here if the mean represents 50% and this is 34%? How much is left in here? Okay, it's only 16%. Exactly. Okay. So the answer to that question is 16% of the population is above 66 inches tall. Okay. Or another way you could look at it, if I were to pick a random person from this population, the probability that they would be more than 66 inches is 16%, 0.16. Okay, next one, less than 60 inches. Okay, well, 60 inches is going to be over here. That's one standard deviation below the mean, so we're interested in this area in here, less than 60, right? And again, 34%. This is 50% of the population from the mean down, right? This is 34%. That's going to leave 16% here. Okay, let's go to the next one.
Could you also add the 13.6, 2.1, and 0.1?
Yeah, you could do that also. Yeah, it'll come out the same way. Exactly. Okay, seems like a lot of work. Seems simpler just to subtract it, right? Okay, the gestation time for humans has a mean of 266 days and a standard of 25, a standard deviation of 25 days. So, okay, we're starting to get a little bit more involved here. I'm going to a fresh piece of paper, and I'm going to draw again. I think it's really worth drawing these things out, even if you think you can do them in your head. So the mean is 266 days. Did I get that right? Yeah. And the standard deviation is 25 days. What percentage of pregnancies would you expect to be greater than 291 days? I'm going to put 291 over here. Okay, what's the difference between 266 and 291? 266,
25.
Yeah, 25. So that's one standard deviation, right? So the percentage of pregnancies you would expect to be greater than 291 days is the same area that we were looking at here, right? So greater than 291 would be the area above 291. So we know that this is 34%, right? So that leaves this to be 16%. Okay. Okay, between the mean and one standard deviation above the mean is 34%. And if we add the other one standard deviation below the mean, it would be 34% here too. Right? But we're only interested in the area greater than 291 days. How about less than 241 days? How far below in standard deviations, how far below 266 is 241? Right, same thing, right? Again, 25 again, right? Okay, so this is minus one standard deviation below the mean, right? So that means that this area is 34, this area is 34, this area is going to be 16% again, approximately 16% again. Okay, what percentage of the pregnancies would you expect to be less than 241 or greater than 291? What percentage would you expect to be less than 241 or greater than 291? Either one of those satisfies you. Well, 16% are less than 241, 16% are more than, so we'd expect 32% of the pregnancies to be less than 241 or greater than 291. Okay, good, excellent, good. We're cooking with gas here. Okay, so let me move this up a little. Okay, so we can actually do this in Excel too. I'm gonna move on here a little bit, and I'll come back. Let's try this first one and see how far we get with it. Okay, assume that the heights of adult U.S. women is mean at 63 inches, standard deviation of 2 inches. Okay, so I'm gonna go over here, start a new page. Okay, so our distribution looks something like this. I didn't draw a very good one there, did I? Okay, U.S. women have a mean of 63 and a standard deviation this time of 2 inches. What percentage of women would you expect to have a mean height less than 63 inches? We know that, that's 50%. Less than 62 inches. Okay, 62 inches. How many standard deviations below 63 is 62 inches? Right? It's only one, right? Standard deviation is 2, but that's only one less. So it's 1/2 of a standard deviation, or 0.5 standard deviations below the mean. Well, we can't use the empirical rule there because we don't have an indication of what percentage that represents. So we need another way to do this. Okay, and the way that we're going to do this is we got 2 ways we can do this. One way is we can go to a table to solve this. Okay, and I think I gave you one of these tables here. Standard normal distribution. It's called a z-table. Okay, this table tells you what areas under a curve, under the normal distribution curve, represent the different z-scores. Okay, so if I look at this drawing, and almost all of them will have a drawing or an indication of how they work. Okay, this one. See, notice that whatever the z-score is, the area that this table is going to tell you is from that z-score to the left. Right? It's not going to tell you the area here. It's going to tell you the area that's in the shaded area to the left of the z-score. If I go to this second page, if you figure out what the z-score is, this is going to give you the area to the left of that z-score. So no matter what you get, it's always going to be to the left of the z-score that you're looking up. So now, how does this table work? Well, you may have noticed me calling z-scores that are less than the mean, I give them a negative number. Z-scores to the right of the mean, I give a positive number. So notice that these are all positive z-scores here, right? Here's a z-score here. These are all positive z-scores. So they all have positive numbers for the z-value. And the areas are always going to be above what number? Since it's above the mean, the area to the left is always going to be above 50%. And in fact, if you look in here, the smallest percentage is 50%. Right there, all of the other ones are bigger. The numbers in here represent the areas. Well, how about the other side? How about to the left of the mean? That's where this table is going to come in. Okay, and in this table, all of the z-scores have negative numbers, and the largest one has a value, an area of 50%. In other words, a z-score of -0. Basically, just the same thing as 0. But in this case, again, all of these areas represent a area to the left of whatever the z-score you calculate is. Do you remember what the z-score was that we just calculated before? Remember the mean was 63, and we want to know the percentage of people that are less than 62, right? Wasn't that what we were looking at?
Yeah.
Okay. Let me get that problem back. Let me get Word back. Here it is. What's the percentage of women you would expect to have a mean height less than 63 inches, 50%, less than 62 inches? Well, the z-score for that is going to be equal to, I can actually use a formula for that. Z is equal to the value you're interested in minus the mean, right? So what is that? That's equal to 62, right? Oh, wait a second, minus the mean. That number divided by the standard deviation, sigma. Okay, so I'm going to do that right here. Yep. So the z-score for 62 is going to be equal to 62 minus the mean, 63, divided by the standard deviation, 2. So that's equal to -1, right? 62 minus 63 is -1, divided by 2, it's equal to -1/2. Right? Or in other words, equal to -0.5. That's my z-score for that value of 62. Okay.
So it doesn't fall within the standard deviation of 2. The one, it doesn't fall. It falls outside of the first standard deviation, right?
Well, it doesn't. We can't use the empirical formula because it's not an even number standard deviation. But that's below it's a negative because it's below the mean. So now I'm going to go to my table. Okay, here's my table. And I'm going to look up what the z-score is, what the area to the left of the z-score is, which is the area I'm interested in. I want to know the percentage of people that are less than 62 inches tall, right? And my z-score for people less than 62 inches tall is -0.5. So I want to go to my table, and I'm going to look up a z-score of -0.5. So here is -0.5, and here's a number right here. And actually, that's the number I'm looking for. It's 30.85%, or 0.3085, if I'm looking at it as a probability. So the area that I'm looking for here, or in other words, whoops, I have so many things going on here at the same time. Let me move this out of the way, see if I can get here it is. The area I'm looking for here, in this case, this area is 0.3085. That's what this area is right here, 30.85%, right? And I got that from my z-table. Let's see if I can't get back to that now. Here we go. Right, I got that from here. Well, what are all these other numbers for? Well, let's say it had come out to be an uneven number, like -0.48. Well, the way this table works is if I want to know what the area to the left of the value for something has a value, a z-score of -0.48, I can start here with the -0.4. The first digit is in this column. First two digits are in this column for the z-score, -0.48. And the second number, the third digit here, 0.4 and 8, is in the columns across here. Now, if you look at the top, this is for adding, like for instance, 3.40, 3.41, 3.42. Each column represents the third digit for the z-score. So if I was looking for the area that represented a z-score of -0.48, I would say -0.4, 0, 1, 2, 3, 4, 5, 6, 7, 8. It would be 31.56%, or 0.3156. That's the way I would use this table. Okay, so in our case, we didn't have to worry about that because we were only looking specifically at a z-score of 0.5. Okay, so now let's go back and take a look at the next one. Here we go. Okay, and greater than 66 inches. What about greater than 66 inches? Let's think about that. Let me go back to my chart here. Notepad. Okay, let's go back to this chart. Okay, now this time I'm looking for an area greater than 66 inches. In other words, this area here, and this is 66. So what's the z-score? How many standard deviations above? Remember, the z-score is really just the number of standard deviations that you're above, sigmas, that you're above or below the mean. Okay, so let's take a look at this. 66, right? Well, one of the ways I said I could figure that out is just look at the difference. 66 minus 63 over the standard deviation, which is 2. So this time, 66 minus 63 is plus 3 divided by 2. So we're 1.5 standard deviations above the mean. It's a positive number because it's above the mean, right? So our z-score here is plus 1.5. That's what z is equal to for a height of 66 inches, right? So what percentage of women in this population have a height greater than 66 inches? In other words, greater than a z-score of 1.5. So let's go back to our table. Here we go. Except this time we're not going to use this table because this table is only for the negative z-scores. We're going to move up and go to the second table, which is for the positive z-scores. So a z-score of positive 1.5, 1.0, 1.1, 1.50. 1.50 is 93.32, 0.9332. So the area to the left of a z-score of 1.5 is 0.9332. Right, that's the area to the left. So what is the area? What percentage of women in this population have a height greater than 66 inches? Not
0.9332.
No, that's the percentage have a height less than that. Right? Remember, the table always gives you. We're interested in the women that have a height greater than 66 inches, but the table always gives you the area to the left, which is 0.9332. So how much is left? Right. So look up how much is going to be left. About 6.7%, right, is going to be left here. Right, 93. If 93% is on this side, that leaves 7% roughly on that side. Right, it's got to add up to 100% of the area. Right, actually it's 0.0668, something like that, if I'm right. Yeah. Exactly. Well, the question tells you what you're looking for. It's asking you what percentage of the women are have heights greater than 66 inches. So in this case, you got to keep in mind the table will only give you areas less than a certain z value. So you have to do a little manipulation to get the value that's the percentage that's more than that value. Okay, let's take a look at another one. Okay, let me get that word back. Okay, the body temperatures of adults have a mean of 98.6 degrees and a standard deviation of 0.6. Okay, I'm gonna draw another sketch to represent that. Let's see what I have. Okay. Try and make this one a little neater. Okay, so we have a standard deviation. Our mean is, of course, 98.6. Right, for this population, mu, for this population. What did we say our standard deviation was, according to this? It is, okay, let's see. It is standard deviation of 0.6 degrees. Okay, 0.6 degrees. Put a 0.6 degrees. Okay, so what's the probability of randomly selected individual has a mean body temperature greater than 99? Right, so here's this person, he has a body temperature of 99 degrees. What percentage of people have a body temperature greater than that? Right? Well, what do I need to know in order to find that area? Well, I know my table will only give me the area to the left of that, right? So I need to know the z-score for that value of 99 degrees. How do I calculate the z-score? It's the difference between the value I'm interested in, 99, minus 98.6, over the standard deviation, which is 0.6. Okay, what is that? That's going to be 0.4, right, divided by 0.6. So that's 2/3. The z-score is positive. Again, it's positive because it's to the right of the mean. Positive 0.667. Right? So now I need to know, well, that z-score, what area does that represent? See where this arrow is? What area does that represent? So I go to my table, and I'm looking now for a z-score of 0.66. So here is a z-score of 0.6. Now this number is 0.60, 0.61, 0.62, 3, 4, 5, 6. So the area to the left of a z-score of 0.6 of 0.67, 0.67. Let me go. Yes, 7 is going to be here. But 0.67 is 0.786. 0.786. Okay, and where is that area? That's the area here. 0.78. I think I got that wrong. I got that wrong. What was it again? 7486. I lost the 4 somehow or other. 0.7486. That's that area to the left here. So what does that leave here? That leaves 1 minus 0.7486. Right? So the area we're interested in is 1 minus that. Okay, so let's see, 1.0000, 0.7486, and that's going to be 4. That's going to be 9, 1. Carry the 1 over there. It's going to be 9, 5. It's going to be 2. 0.2514. 25% of the people have a temperature greater than 99 degrees Fahrenheit. Right? 74% of them, about 75% of the people have a temperature below 99. About 25% of the people have a temperature above 99. Let's try another one of these. Okay, now where did my Word document go? Here it is. What percentage of people? I'm gonna go to this one. I'm gonna go to this. Less than 98 degrees Fahrenheit. How about that? Okay, so less than 98 degrees Fahrenheit. Okay, here's 98. So this area in here is roughly 25%. That area is roughly 25%. Now I'm going to take a look at 98 degrees Fahrenheit. That's below the mean. So that's going to have a negative z-score. So what is the z-score for that? Z-score is going to be equal to 98 minus 98.6 divided by the standard deviation. So the difference is 0.6, and the standard deviation is 0.6, so it's 1. It's negative 1 standard deviation below the mean. Okay, so what percentage of people have a body temperature that's below 98? Well, I can find that area, that proportion, that probability, by going back to the table again. Okay, except this time I'm going to use a table for negative z-scores. And my z-score is negative 1.0, so it's going to be right here. That's going to be 15.87. 0.1587. This area, even though I didn't draw it very well, is 0.1587. 158. Okay, so 15.87, about 16% of the population is going to have a temperature that's less than 98 degrees. Well, okay, so we determined 25% of the population has a temperature above 99, and 16% roughly has a temperature below 98. What if I asked you what percentage of the population has a temperature between 98 and 99 degrees? Well, gee, we know that this area here is roughly 16%. This area up here is 25%. So between the two of them, 41%. And the area that we want is the area that's left in between here. So what's that going to be? That's going to be 59%. Right? Because that's the only thing that's left, is the area between 98 degrees and 99 degrees. Okay, I didn't sketch it proportionally. That's why it looks a little funky, but the numbers are right. That's the way it comes out. Okay, you guys okay with that? Uh-oh, I see an oops there. Everybody agree with me here? Did I make a mistake? Okay, good. All right, good. I think I got it right? Okay, so now let me give you another trick here. Not only do we have this table that makes us capable of doing these calculations for normal distribution, but we also have functions built into Excel that'll help us out with this. And on Blackboard, you'll find excuse me, you will find a reference cell for Excel. Oops, I got the wrong one. Okay, let me open that up again. I'm gonna have to move all this stuff out of the way to get to it. Where'd it go? I lost it. There we go. Okay, good. Excel functions. Okay, I'm going to open it up here. And if we look at these Excel functions, there's a whole bunch of them. Okay, there's one called norm sdist, there's something called norm dist, there's something called norm inverse, and so on and so forth. I'm going to pick one of these out. And the first one I'm going to pick out, these are what the inputs that it's going to ask for. And these are going to be the results. So for instance, if I use the function norm sdist, parentheses, it's going to ask for the z-score. Remember the last z-score that we were looking at was -1, right? So -1. I'm going to put in -1 for the z-score, and I'm going to hit enter. Oh, look, 15.8. That's the same thing we got when we used the table. How about the other z-score? Equals norm sdist. Okay, that one was a plus 0.67, right? A plus 0.67. Same. Yeah, I could do that. It'll let me put in that. Let me do it even more accurately than the other table would, right? Plus 0.667. I'm going to hit enter, and there's our 74.76, right? And then what did we do? We figured, oh, well, wait a second. The area I was interested in over here was the area to the right of that, so it was equal to 1 minus that, which is where we got our 25%. And then to figure out what was in between those two, we just took this one and this one, added it together, and subtracted it from 100%. So we could use Excel to translate the z-score into an area for us. Okay. What about these other functions? How about this one? Equals norm dist. No sdist, no standard distribution. What's it ask for? Oh, it asks me for x, the mean, and the standard deviation and cumulative. Okay, I'm going to fill this in. Let's say, for instance, I was looking at the problem we just did. I was looking for 98 degrees, right? Comma, and the mean was 98.6, and the standard deviation was 0.6. Filling in what it's asking me for, and ask me for cumulative. Since we're always looking at areas here, the answer to cumulative for this particular function is always going to be true. I'm going to hit enter, And look, it gave me that value. I didn't even have to figure out what the z-score is. It gave me the area to the left of that value. Okay, that's for norm dist, right? And you can use these other functions similarly to solve these various problems, right? And it'll help you figure out what these various areas actually represent. Norm dist, norm s dist, norm inverse. Let's say, for instance, that you know let's say I were to ask you, for this example, I were to ask you, what temperature would I expect 80% of the population to be under? Right? I want to know the temperature out here, where 80% of the population would be less than this temperature. Right? So that this area to the left would be 80%. Only 20% of the people would be above that temperature. Let's see what we have here on Excel. Excel actually has a function called norm inverse. And I'm going to type it in here, equals norm inverse. Does the inverse of that, changes an area into a value. Okay, so what's it going to asking me for? It's asking me for the probability. Oh, the probability is excuse me, the area under the area to the left, which is 0.80, comma, the mean, which is 98.6, and the standard deviation, which is 0.6. So what value of temperature represents the value at which 80% of the people are below that, and only 20% are above that? Well, 99.1 degrees. See how flexible these functions are? They can really help you figure a lot of this stuff out. Okay, so the last one is norm S inverse, which just gives you, if you put in the area of the curve to the left, it'll give you just the z-score. So for instance, if I were to put in here, you probably won't use this one as much. If I were to put in norm S inverse, and it's asking you for the probability, so 0.5, I want to know what the z-score is for 50%. In other words, 50% of the area of the distribution is below that. Well, what is that? That's the mean, right? What's the z-score for the mean?
0.
And there it is, 0. Right? Z-score for the mean is 0. Right? Z-scores to the left of it are negative. Z-scores to the right of it are positive. Okay, so I mean, there's a lot of ways. There's an old expression. I don't know if it's used very much anymore. A lot of ways to skin a cat, right? So there's a lot of ways for us to solve these problems. But one of the things I might caution you is that even if it looks simple, it always pays to make that sketch first, so you can get an idea. I'm going to undo that. Right? It always pays to make that sketch first, so you don't get confused about the areas that you're working with. Let me see if there's something else here I want to make sure that you see. That's a z-table, z-distribution, and you have some other sheets here where I've given you some additional examples and so on and so forth that you can go through on your own